This is going to be a quick tutorial on how to do Project 4 in ANSYS Fluent. It's about finding the boundary layer on a flat plate. So as usual, we start in Workbench and use this fluid flow Fluent, and we would drag that in. I already have it here, so not going to do that. Then we go ahead and click on Geometry, make sure that it's set to 2D, so it's this right here. And then we'll go ahead and import geometry. I already did that, but you just go and it would say import geometry instead of replace geometry, and just go ahead and select whichever one. And then we can mesh. I already have the mesh open, but you would right click, click edit mesh. And here's the mesh that I did. Went ahead and inserted a method, did triangles method, reduced the mesh size to 0.006 meters, and then added an inflation region around the flat plate by selecting the wind tunnel geometry for this part, and then selecting the 4 edges of the flat plate for the boundary, so all of these edges. And then went ahead and increased the maximum layers to 20 and the growth rate to 1.4. And then once all of that was set, I generated the mesh. This is what came out of that. And then added all of the name selections, so the velocity inlet, the pressure outlet, the wind tunnel walls, and then the 4 sides of the flat plate individually, so that later on we can pull information just along one of those surfaces. And that's all we need to do in terms of the mesh. As you can see, we've got a little bit of a better region around the flat plate itself. So now that we've done our mesh, we can go back to Workbench, and we would right click setup and click edit. Already have Fluent open. Just make sure when the window to open Fluent pops up, you check the box for double precision. So already got some of the stuff here. You can see the residuals out of the solution. We made sure to turn on energy, and we kept the viscous at K epsilon. You could also probably do this with laminar, since the flow along the plate is going to be a laminar flow. It's not getting into the turbulent region. Also made sure that the density of air was set to what we wanted it to be at, which was 1.204. And then changed the inlet velocity to 2.44 because we were at a 40 hertz setting on the wind tunnel for the lab. And then just added a report definition. For drag, you do new force report and then click drag, and then you change it to drag force. Just rename it. And that's so that we can pull information to get the drag coefficient of the plate later. Fluent does calculate that itself, but it's better to non-dimensionalize yourself. And then we went ahead and did a hybrid initialization and ran the calculation with 300 iterations. And this is the residuals that came out of that calculation. Next up, we had to add surfaces so that we could get the velocity profiles at the 3 locations on the flat plate at 0.2 centimeters, 8 centimeters, and 16 centimeters. So for each of those, just have to add in the x coordinate of that location along the flat plate. For my wind tunnel, my initial line was referenced from the front of the wind tunnel, so it was 960 millimeters to the beginning of the flat plate, so had to adjust for that. And then Y I just did from the top of the flat plate, which my flat plate had a little bit of thickness, but it was pretty thin, so this is the top of the flat plate, and then I did it to 0.05 meters just to make sure I covered all of the potential velocity boundary layer. And then I made it a rake and used 500 points just to make sure that I got enough data out of it. And then did the same for the 8 centimeter line, just with a different x coordinate, and for the 16 as well. Next, we added the contour for the velocity. We needed it with vectors, so first thing we did was to get the contour itself done. As you can see, there is a little bit of thickness increase of the boundary layer. It's kind of hard to tell, but it's a little bit visible. And then we added the vectors as well. I scaled them down just so that it wasn't overcrowding the contour. You can see kind of how the boundary layer is developing. And added both of those into a scene to get the overlay, so I just turned up the transparency a little bit because the arrows were blending in too much with the contour itself. But you can kind of see how that looks. And then next we need to do all of the XY plots for the velocity profiles so that we can export that data and graph it in Excel. So we're going to use those surfaces that we created earlier, the lines, the vertical lines along the flat plate. I wanted to export the position on the y-axis, so I checked that box. And then you need to export the y coordinates, so change the x to a 0 and the y to 1, leave z at 0, and then change the function to velocity. And then you can go ahead and plot that. You can see it there. And then you would just write it to a file and give it a name, export it. And then you can open those coordinates in Notes and paste them into Excel. And we did the same for 8 and 16 with those other lines that we created earlier. And then the final thing that we need to pull out in an XY plot is the wall shear stress, so that we can get both the wall shear stress and the skin friction coefficient. And we're just going to pull the wall shear stress along the top wall of the flat plate. That's why we labeled them separately earlier. So selected the top wall. We do want it with respect to the x position this time, so leave the x at 1, y at 0. And then under the y-axis function, we choose wall fluxes and then wall shear stress. And then we would do the same and just write it to a file. Already have done that, but this is kind of what that looks like. There's a little bit of a jump at the front just because of the edge of the plate, but and then the final thing that we can get out of Fluent itself is that drag force that we added the definition for earlier. So we can go ahead and click compute, and then it spits out the value over here. So we've got 0.136 newtons of drag. And that's about all that we got to get out of Fluent, and that we just add to all of the graphs. So I'll show a couple of the graphs just for the sake of it. So here is the comparison of the wall shear stress versus the x position, and we included the Blasius solution as well. And then we have the same for the coefficient, the skin friction coefficient, but instead of against the x position, it's against local Reynolds number, but you can see the trend is very, very similar between the two. And then the boundary layer thickness, we just tabulated that out by comparing the EU free stream velocity, which in our experiment was about 7.0 9.8, but in the simulation it was about 7.02. And you compare the free stream velocity with the velocities that were output for the velocity profiles, and when that ratio is 0.99, you call that the boundary layer thickness. And then we've got the drag coefficient as well. Our drag was a little bit higher in the simulation, but that's because the simulation has a little bit less precision because the mesh still could be better. We did the refinement region around the plate, but can always be better. And the lab equipment wasn't fantastic either, but there's going to be error. Don't worry too much about it. Fluent is going to do its best for you. That is all. Thank you for watching, and have a good one.